So let us briefly wrap up our lecture. Unavoidable errors in computing. So just a brief definition so that we recall what are the typical errors. So we have two types of errors. One is a truncation error that happens when we are implementing a mathematical formula or any formula that possibly has a very large or infinite number of elements. For instance, here there's a sum that mathematically can go to infinity. And on computers, we can't go to infinity, so we kind of at some point have to chop it off. So then there is a difference between the actual formula and the one that we implemented, and that results in truncation error. Typically, it's not a big deal, because in all of these formulas, if they actually converge and actually give us a proper sum, at some point, all of the values for these very large numbers will kind of die out and be very small, and we will not really notice a huge difference in practice. For one of those things is that one thing that we also chop off, a round of error, there's digits to the right of the decimal are discarded, so whenever I have a number with an infinite number of digits, at some point I gotta stop, and that's what I can fit. There was news yesterday, it was a Pi Day, because it was 3.14, 14th of March, and there was a researcher, and I forget her name, that computed pi, like she pushed the record in computing the number of digits, and it went up to 31 billion. One part of me wants to say why, but it's cool because you can't store them in a computer, so you kind of have to have a way to come up with what that digit is. So it's obviously, if you're going to 31 billion, it's something, right, to get that. So anyway, that number where we push the record, we kind of have to store all digits separately. And to store them separately, how many bytes does it take to store 31 billion numbers? If I'm doing it in binary form, what do I have to decide first? Yeah, how many bytes per digit? Since they're digits, I can go with 1 byte. There's 0 to 9. Right? You can figure that out in 1 byte. So it's 31 billion bytes. Billion is 10 to the 9. Yes. So 31 gigabytes to store 5. Okay. So that is part of what we've actually gotten through. So we have to have a system of how we are going to store a number, and then basically just no matter what the system is, you have finite space, so something will have to be chopped off, and that is typically what we call round-off error. This error can happen both with storing the number itself as well as a result of an operation. So there could be a case that you can have a number that you're storing perfectly fine and another number that you're storing perfectly fine. Here are 2 examples. But once you want to put these numbers together and perform an operation, the result of that operation, you don't have enough digits to store correctly. We're going to go through that a little in a little more detail by the time I get through a review. So how do we measure errors? They could either be absolute or relative. Typically, if I'm working on one problem, measuring absolute errors are just fine, but if I want to compare 2 different problems, then it's important to actually do relative error. So basically, if I'm measuring length of a bridge versus river, obviously one is shorter than the other. So then absolute measurement error of 1 centimeter is a different thing when I'm talking about something that is shorter versus something that is longer. So that's why we introduce relative error and divide this absolute error by the value of what I'm actually measuring to get the percent error that I'm making. So here, true value is great when we have it. If we don't have a true value, then we're using the best approximation we have for the true value. Okay. So back to digital representation of numbers, we store different numbers differently. So we have integers, real numbers, and complex numbers. And if there's a fundamental difference between integers and real numbers. Complex numbers are really two real numbers. So once I decide how I store the real numbers, then I just need twice that to store a complex number. So integers, we typically have to basically just get the integer, and first thing that we want to decide is how much space do I have for the integer, and the second part I need to decide is, do I have space for negative sign, or do I want to store negative integers or not, because that decides of what is the range that I'm storing. So for instance, if I'm just using 1 byte, and 1 byte is a group of 8 bits, each bit in computer language is 0 or 1. That's basically, am I off or on? That's what computers can understand and execute. They don't have 10 fingers. So we have learned that we can actually represent every number in a base where I only have 2 digits. Actually, I can represent any number in any base. But for computer, it's this binary system that is the important one. Okay? If I had a way to express 3 digits somehow in a computer, then I could keep going, but we only have on and off. Okay? So basically, let me just, in terms of understanding, what we figure out for any number is basically we take powers of the base, in this case powers of 2, and try to find the largest power that can fit into the number. Then that's the largest power. So for instance, in 25, it's 2 to the 4. Okay. And then I have the remainder. I fit the largest power into the remainder. In this case, it would be then 8 and then plus 1. So then I realize that for each digit, I start from the right, and I basically put my 0th power of 2, and whether I have it or not, so it's 1. Then I don't have this first and second power of 2, so I'll put zeros. And then I have power of 3 and power of 4. So that is my binary representation of a number. It looks odd, however, that's precisely how we are storing regular numbers. 25 is 2 times 10 to the 1 plus 5 times 10 to the 0, so it's the same system. I'm just having this multiplier that can be between 0 and 9 if I have a base 10. And in our binary system, the multiplier is 0 or 1. Right? So it goes up until 1 less than the base. So I can convert any base number. We are very much used to base 10, and that's how we think, and it's kind of our second nature at this point. But any other base could work just as well. Okay? So 11001 could be a number in base 3, right? And then I would have multipliers 1 and 0 and 3 to the appropriate power. Okay? So that's the part that is possibly confusing, but again, in practice, what we need is binary versus not. Yes?
Sorry, I have a question. Whenever you're doing, for example, base 8, and let's say that you have 2 numbers of 1 power, could we put a 2?
You'd never have 2 numbers of 1 power. Each spot is precisely unique power. So it's 1, 1, those are 2 different powers.
Okay, so
it's never 1 power. No. And that's why you're fitting the largest you can in order to make that unique. And that's why you don't have, in base 10, you don't have a digit 10. You have digits 0 to 9. Because the moment you would have digit 10, 10 times 10 to the 1, it's 10 to the 2. So that's 1 times 10 to the 2. And you don't want to have that ambiguity. Okay? That's precisely why your digits are 1 less than the base. Yeah. Otherwise, you wouldn't have uniqueness. And then once I'm storing that, so I decide whether I had 1 byte or 2 bytes, and then I just start storing the number. This is actually 173, I think. Yes, 173. So basically, I just give myself space and store all the ones and zeros. And if my number is signed, then I actually have 1 bit reserved for that sign, and I have to know that. So the important part is that I have to know what is actually stored in memory in order to be able to read it. And another thing is that we have to have, so once I can store signs, I could technically have positive and negative 0. That's a waste. I mean, it's fine if I can have 2 ways to represent it, but that's a waste. So there's an agreement to take one of those, negative 0, and basically map it to minus 128 to actually enlarge the range. And if I had unsigned bits, then I would have a 0, so all of my space would be able to store the number. So then my range would be 0 to 255. 255, the largest numbers, is if I put all of the digits be 1. Okay. So if I have real numbers, the situation is completely different. So first we actually kind of, in binary, but we're just going to work in the regular thing. In the base 10, we're not going to convert this, and we're not going to do a practice of converting a real number to its representation, but just so you understand, okay, scientific information is important so that everything is kind of normalized to the same system. Okay? So in this case, for binary, our scientific notation requires a number at the beginning that is larger than 1. If I do that in base 2, well, then there are no digits more than 1, so we will always have 1. So we take that scientific notation and we understand that it's 1 plus something, and we always store only that something, p. Okay? And then I have times 2 to some exponent, because my base is now 2. So that is my scientific notation in binary world. And I focus then on storing p and t in this scientific notation. There's no need to store base 2 because I know the base is 2, right? So I focus on storing p and t, and then question is, well, how much space do I have? If I have 32 bits, then we will say 24 bits for p, which we call mantissa, and we will store, we will use 8 bits for exponent t, and that includes sign of both. So both could be signed. If I have 64 bits, or so-called double precision for real numbers, then I will have 53 bits for p and 11 for t. And so if my number, my mantissa p, has too many digits in the binary world and they don't fit into these 53 bits, well, too bad. Okay? So essentially, this is where that round-off error happens. And if I was adding 2 numbers that have vastly different exponents, in decimal world that would be 10 to the 9 and 10 to the minus 9, the result of that operation has to have the same exponent. So I gotta pick 10 to the 9 or 10 to the minus 9. It's gonna be 10 to the 9. And that's where suddenly my mantissa has way too many digits that possibly don't fit into the memory. Okay? So I will get largest numbers if I store the largest mantissa all once that I can, and the largest exponent, so I will get the limits on what we can store. So then once we actually have the complete picture of what can be stored, what cannot be stored. 0 we can always store no matter what, we just zero everything out. And then there's some smallest number. There's some smallest number, the least negative exponent that I can actually do. That's going to give me the range, like what the smallest number I can store is. But so there is a gap of numbers between 0 and that smallest number that I cannot store. That's called underflow. Same thing on the positive side. There will be the largest number I can fit if I put all ones for everything, exponent and mantissa. And that translates to some number that is approximately, of course we don't have all the digits for it, but those are approximations out there. And above that, I can't store that number. So that's called overflow. And simply errors, you get junk result. Happens. Now, in between, there's these little lines. What they indicate is that I also have gaps between numbers that I can store. If I can only store real numbers down to 16 digits, then there is a gap for all of the numbers that have 17, 18, 19, and more digits, okay, in their scientific notation. They're not stored correctly. They're rounded off. So there is not in all numbers are continuously represented in the computer. There are small gaps in between everything because of the round-off error. Okay. So there's all of this has little gaps of numbers that have been rounded off. Okay. So one example, just to so basically this is just to repeat again, if I add or subtract numbers that are close together, I could get this result that gets rounded off. And because of that, not stored. So if I have, for instance, 10 to the 10, I use 9, or 10 to the minus 10. I have to represent that as a single number that has single exponent and single mantissa. And in that sense, typically, in that case, the smallest number typically just gets rounded off and disappears. Okay? So then if you actually do some calculation like this, you might get a 0 because this first one is 10 to the 10 because of the round off minus. Though computers these days are actually sometimes programmed to actually figure this out and go and investigate what is, and basically group the numbers that are similar in size first. So for instance, in this case, it's going to figure out, oh, these are similar in size. Let me add or subtract those first and then proceed. And you will have in your example of a quadratic formula where there's possibility to add or subtract close numbers, and that results in errors. Okay. So just as a review, which I've been doing so far, we're used to decimal system. However, a decimal system is not useful for computers. We could have any other base. For computers, we typically use base 2. And we have to express numbers in terms of powers of 2, 1, 2, 4, 8, and so forth. And that is our foundation for representing the number on a computer. And so just as an exercise, how about you all do 158? I've been talking a lot. What is 158 in base? Well, how would I represent it using 16 bits? Number on a computer. So you have to convert it to base 2 and then figure out how it's going to sit in the memory. Yes?
For the one for base 8 and I would say if you want to represent, let's say 18, and 64 is too big, 8 is too small, and we can do 2 numbers.
In base 8? Yes. So base 8, you can have 2 of those.
Oh, okay.
That's base 8.
Yeah.
It can have digits 0 to 7.
Okay, there you go. Okay.
Yeah, okay? So I'll do that calculation right here.
Yes.
So 18 in base 8. So that's 2 times 8 plus 2, right? That's 1. Okay. So this is your 8 to the 0. This is your 8 to the 1. So that's 21 in base 8.
And it could go up until number 7, right?
Go. Yeah.
No, you mean 18.
18 in base 10 is 21. 22 in base 8. These are my digits. And in base 8, they could be 0%. How's 158 going? None? So this is my number in base 2 as starting from the, let's start from the right, 0, 1, 1, 1, 1, 0, 0, 1. How many digits is that? So if I have 16-bit number, I'm going to also place 8 zeros at the beginning. Okay. Now, that's unsigned integer. If it's a signed integer, then that first one would be 1 if it were negative, but it's not, so it remains 0. Okay. Okay. And then in real numbers, I have this scientific format in base 2, and since it's always larger than 1, that's rules of scientific format, then then I don't store that 1, so I store just the rest of it, P and T. And basically, if I have single precision number, I have 32 bits altogether, so this is how I split them between P and T. And if I have 64 bits altogether, I do 53 for mantissa P and 11 for exponent T. And both mantissa and exponent also have a digit in there. Digit for the sign. Okay. And then, can I properly represent 0.1 times 10 to the 708? Can that be done? About 308 is the largest exponent I can do. So in double precision, it's going to result either way in overflow, and it simply causes an error. Similar for the negative version of it. Okay? So let's actually do this exercise to wrap this up. So let's find the smallest number I can add to 1 and still have a result larger than 1. Does that make sense? 1 plus some delta is always larger than 1 in math. However, at some point, delta will be so small I will not be able to accurately store it. So let's find what that is. Let's test. That's called machine precision. And this is, you're just going to find the approximation for it. So create a little script in your notebook, distributor notebook, to get reasonably close to this number. You can't precisely pinpoint it, but you can kind of investigate where it's at. So figure out some sort of a loop that will create that number smaller and smaller and smaller and test it, and then report back when. Which loop is the most appropriate? While. I've heard while somewhere. Yes, because 4 would be appropriate if you knew how many times to do it. You do 4 with a break, but while is cleaner. More robust programming. So what are we going to do to find this? Can anybody instruct me? I don't know what I'm doing. It's Friday. There's a delta. What am I going to, it's Friday. I don't want to type a lot. I'm going to call it D. D is equal to, you got to start it off with something. These are computers. They don't read mine. 1. Great. That works. Now what? Somebody said while loop. While what? I want to test when this breaks down. If D is 1, it's going to be 2, and that's larger 1. But at some point, that's not going to be true. And then here I can divide make it smaller somehow. Dividing it by 2 works.
If you raise it to the negative power,
You could try that. How about you try that? I'll try this and see how quick. I mean, it's all are these are approximation. I could divide by 3. I could divide by 2.1, right? I can divide with 1.1. That will probably get me a little closer. Right? And then print D. That's it, actually. I'm actually gonna print that D within the loop before I divide by it, just to show all of the numbers how they get smaller. And then somewhere around what's equivalent to 10 to the minus 16 is where that mantissa of 53 bits is not enough to store D because D is too small. Okay? Or just imprecise. And then it gets zeroed out. And that's because I'm trying to do 1 plus D. Okay? And I gotta store the result of that using scientific notation, right? In itself, this number can be stored in many more smaller numbers. I can go to the 10 to the minus 308 if I'm storing single number. But if I'm doing a result of an operation, 1 plus this number, since that result has to go into the memory as a single number, and there's in exponents, there's 10 to the 16 times difference. Right? In exponents of 2, that's even more, right? So there's orders of magnitude difference, and because of that, I can't fit it into the same number. Is this clear? So this is the result of an arithmetic operation. This is... Now, what did you get with, what did you divide with? You're still going? I'm going to actually comment on it and just print it at the end. So this is slightly actually technical. The last one is the one because I divided by 2 after that wasn't possible anymore. So this is the last one I can do. Below that, so it's somewhere between 1.1 and 2.2 times 10 to the minus 16. Now let's divide by 3 and we'll see what we're going to get. Are we going to even see the difference? Slightly different, right? If I divide by 1.1, slightly different. So none of these are precisely the number. I'm just getting close. It's just that at some point it's going to be too small. So what I divide with does not matter as long as I consistently get smaller. I cannot find this limit precisely. So whatever I do is an approximation, but it still gives us an idea of how different the numbers can be so that when I'm adding them. Okay. Okay. So as a summary, we can't avoid errors. There are ones that we can. Those are the ones that we type in. But there's a lot of errors that I cannot avoid because we use finite space to represent numbers. So there is infinite space to represent finite time, if you will, to compute something, to represent formulas. So those are the two main types of errors. One is roundoff, when I'm placing the number into the memory. It can happen with the number itself, as well as the result of operation on two different numbers. Or I can have truncation error, where I simply have to stop in some formula representation while fitting it into my program, and that results in a consistent truncation error. We can, however, estimate those, and there is a field of numerical analysis that's all it's doing. It's trying to basically figure out what is the size of these errors and can we predictably say what the errors will be. The methods that can be analyzed in that way, so you can have immediately an estimate of what the error is, are the best methods because they're stable and more general. So you know that you can use it in certain situations. Otherwise, you kind of just try. Okay? When you don't have those error estimates, you give it a go and see whether you're getting a good result. So it's always important to compare your result of computation to something that you know. And we kind of constantly do that in homework. Okay? And that's something that we know could be a value that we know from an analytical formula, in rare cases that we have that, or it could be actually a result of an experiment. So both works. All right, so that basically ends our lecture 4. After, I hope you have wonderful spring break. After we come back, then we will start a new lecture on actual numerical method for doing something, finding roots of an equation. And if you're also in thermodynamics, then possibly you have already used some root finding already in those calculations. All right.
I'm getting out of here. It's a good one.